Okay, it's my great pleasure to introduce Gopal Gupta from UT Dallas. He's visiting today and as part of a visit for the Alumni Association in Washington, I believe. And he will give a talk on logic co-induction and infinite computation. And as you heard before, if we ask more questions, we can get much more information on other projects, exciting projects as well. So thanks.
Thank you. Okay, thank you, Nikolai, for arranging a talk on such a short notice. So you can see a whole bunch of people who have contributed, and I actually have an alumnus from my lab, Vinay Ahuja here, who's been at Microsoft for many years. Remember, we worked on RoboSoccer. And the idea was that I can model the players on a football field and the passing of football as a constrained system, and basically solve the constraints. And I have the optimal way of sort of passing the ball. So still remember, a very interesting project. So what I'm going to do is so there are many people involved. So the people in red are currently PhD students in the lab or postdocs. So a whole bunch of postdocs and PhD students. And the original work was actually done on which a lot of this stuff is based. Essentially, what I call co-inductive logic programming was actually done by Luke, Ajay Malya, and Ajay Bansal. So what I'm going to do first is give you a one-slide introduction to, this is also the computer science department head. I need to tell you a little bit about my department. So UT Dallas, you probably have not heard of UT Dallas, I guess, maybe it's too far away in Texas. So it's founded in 1969, less than 50 years old. It's actually done very well. It's really a tech university, and it's ranked number 21 in Times of London ranking. We all love rankings, right? So university is younger than 50. So you can see that in 1 year, we'll drop off this list. And in fact, we became number 1 because there are 2 other universities who are ahead of us, became older than 50. But hey, we're number 1. So we're 28,000 students and really focused on computer science, engineering, technology science, and management. And computer science department is actually very large. As I say, everything is big in Texas. So we're actually the 4th largest computer science department in the whole US. If you take out the online program from Georgia Tech, we're actually the 3rd largest. So about 3,500 plus students, 2,400 undergraduate. We have a very large professional master's program because of the large industry around us. So I think DFW area is the 4th or the 5th largest concentration of high-tech industry after Silicon Valley, Seattle, Northern Virginia, and Boston, I suppose. We graduate about 1,000 students every year between masters and undergraduates and PhD. They're actually more than nearly 1.5, 1.7% of the US output. So one school producing that many students. We have 90 faculty members. We do a lot of research, and 37th in US. We were ranked 21st in LinkedIn placement ranking, which basically tracked, this was published once 3-4 years ago, what percentage of alumni work in top companies such as Microsoft. We are known for our research in natural language processing, software engineering, and real-time systems, cybersecurity. And I believe there are hundreds of UT Dallas alum who work actually in Microsoft. The number may be as high as 400, 500. So I have the alumni event tonight, so we'll find out. And there are probably 1,000 alumni in this area. Hundreds of them here, hundreds of them in Amazon and other places. Okay, so let me get started with so first I'm going to give you a little bit of background on, so co-induction, I'm sure all of you know about induction, right? We studied it in high school, in college, and we live and die by it in computer science. But probably not many of you, unless you're working in verification or something, you probably not heard of co-induction. So let me give you a few sort of background or stories about how I got there. I had never heard of co-induction myself as well, till I got started on this project. So I was teaching logic programming. So when I was recruited as a faculty member in the early 90s, one of the reasons I was recruited was because this group had gotten a grant for teaching declarative programming. So essentially teaching programming via declarative languages to first-year undergraduate students. And their innovative idea was to use logic programming as well. The logic being that, hey, you can program database type of applications, right in the first class. And nobody knew logic programming in that group that got the proposal funded. So that's how they hired me because, they need somebody. That's how I got my job. So, there are strange ways in which people get jobs. So when I arrived, I started teaching the freshman students, and the course was structured where We taught ML, functional language, we taught Prolog, and then we taught C, so sort of 1/3, 1/3, 1/3 over a 2-course sequence. And when I got to, so when I was teaching logic programming, so taught them circular linked lists, right? So you have standard data structure in, and then I wondered, how can I have circular linked list in Prolog or functional programming? So that was one question that I had in my mind, so that sort of got started. And then in the mid-90s, my PhD student Enrico Pontelli and I worked on modeling timed automata with logic programming and constraint logic programming. And you can see, if you've done any work in timed automata, then you probably recognize this picture of, train controller gate modeling of at a train crossing. And these are omega automata that run forever. So we use constraint logic, and they have stopwatches because they're timed. So we wanted to verify properties of these timed automata using modeling them in logic programming, and we'll see more details later, and using constraint logic programming for modeling the time constraint. But the challenge was that we used logic programming. How many of you know Prolog or are familiar with Prolog? Okay, everybody, wonderful, or most of you were wonderful. So the challenge was, how do you model the infinite aspect? And we really could not answer that satisfactorily. So what we did was we sort of modeled one run of the train through the system. So we considered that finite string and basically tried to prove all the properties for one run of the system, but really didn't have a satisfactory. Then in 2003, 2004, these 3 PhD students joined my group, 4 actually. And Luke was interested in functional programming and process algebra, and so he started looking at these things, and he stumbled on this book called Vicious Circles. You may have seen it, some of you. And this book is actually by John Barwise and Larry Moss, and some of my talk is actually, the introductory part is from this book. And so Luke actually tried programming infinite streams in logic programming using some of the ideas there, and he didn't see much in it, and he filed it away. And these guys were really bright, and they continued discussing co-induction, but they never told me. So one day we all got together and we were discussing this. They told me about co-induction, and then the light bulb went off, and I could see the solution for how we can model circular linked lists in logic programming and manipulate them, and also the solution for this omega automata problem. So we developed the idea, and we submit the paper to ICLP 2006, which actually was here in Seattle, part of Flock, 12 years ago. The paper was rejected. We lodged a protest. And so, I've been involved with the logic programming community since 89, 88, something like that. So, they were nice enough to actually consider my protest, and they actually reviewed the paper again and accepted it. And in 2016, the paper actually got the 10-year Test of Time Award as the most influential paper over 10 years. So you can see how bad the prediction is for example, best paper award in a given conference or papers that get rejected, right? So, and actually the team was very good. They won many other best paper awards as well that I'm not going to dwell on. So, okay, so now let's come back. So with all this prelude, let's come back to talking about, so the idea as to how do we model circularity in mathematics and in computer science. So if we look at circular phenomena in computer science, then circularity has dogged mathematics and computer science ever since set theory was first developed. So you all know the story of how Frege came up with first order logic back in 1879, predicate logic. So he writes his book, so also what could be called naive set theory. He sends it to Russell, and Russell studies it, and he immediately finds a problem with it, which is known as Russell's paradox. I'm sure all of you have heard of Russell's paradox. So basically, it goes like this. I'll quickly explain it anyway. So think of set of all pencils, for example. Then does the set of all pencils contain itself? The answer is no, because set of pencils is a set, and elements of that set are pencils, and a set is not a pencil, therefore it does not contain itself. So the set of pencils does not contain itself. Now consider the set of all objects that are non-pencils. Now, does this set of non-pencils contain itself? Any thoughts on that? It does, because a set is not a pencil, right? It's a non-pencil. And we're talking about set of all non-pencils, so this set contains itself. So you can actually build sets that contain themselves, and then
set of non-pencils is not a set.
So exactly, but in the naive set theory of Frege at the time, you basically had freedom with language, so you could basically say anything, and that's what Russell pointed out exactly. So then Russell used this to build this set. So R is a set of all sets X. X is a set that does not contain itself. And you can see that if you ask the question, is R contained in R? The answer is both yes and no. Because if R is in R, then R cannot contain itself, right? So R should not be in R. And if R is not in R, then R must be in R. So that's basically Russell's paradox. And then, of course, you've heard of liar paradox. If I say I'm a liar, am I a liar or truth teller, right? I don't have to explain that, right? I'm a liar, so I must be lying. So this statement must be false, so I'm a truth teller, et cetera, et cetera. And there are many such paradoxes that you can actually look at this book by a book called Vicious Circle and essentially see many, many more paradoxes. So then the mathematicians really got spooked, if you remember, and Russell and White had actually wrote these tomes that they tried to justify mathematics from first principles. And basically, Russell put the blame squarely on circularity, and he actually sought to ban it from mathematics. And he wrote, whatever involves all of the collection must not be one of the collection, 1908. And then, of course, Tarski comes along. But then there is this question of if you have a language and you want to reason about that language, then that's sort of circular, right? So Tarski proposed that we cannot have a language that can reason for itself. You really have to have another meta-language that reasons about this language. If you want to reason about the meta-language, you have a meta-meta-language, and so you essentially have a hierarchy of languages. So there's a very famous paper by Kripke who challenged this in 1975. He argued that circular phenomena are far more common and circularity can simply be banned from mathematics. And circularity, if you think about it, has been banned from automated theorem proving and logic programming through the Akers-Check rule. And what does the Akers-Check rule say is that if you try to unify a variable x with a structure that contains x, so x equals f of x, this unification must fail. So we're trying to prevent circular structures, essentially. So it's not allowed, and in logic programming as well. So the question is now, if we allow circular structures, and what if we allowed this unification to proceed, what will we get, right? Now, logic programming systems always actually allowed this for efficiency reasons, because they said, well, checking, you might have x bound to a very large structure, like a huge tree that contains x as a leaf node somewhere. So checking that x occurs in this structure will be too costly. So let's leave it to the programmer to make sure that there is no Akers-Check problem. So you can actually build these structures. The problem is that, you can hold them in memory, but the moment you touch them, you go into an infinite loop. So you're not supposed to have them. So logic programming systems always had them, but you could not do anything with them because there was no proof theory to go along with it. So if Akers-Check is removed, we'll generate circular infinite structures. So if you write something like, so this is the list which says x is bound to a list whose elements are first 1, 2, and 3, and the rest of the list is x. So this is really a circular linked list, right? X is a pointer. Think of it as, you can express these in Prolog, or you can write x equals f of x. Such structures arise in computing, right? We have circular linked list, but we can't model them in functional programming or logic programming, right? As I said, these circular structures are allowed because logic programming Prolog systems do not do an Akers-Check, but you can only hold them as data structures in memory. You cannot do anything with them. You cannot reason with them. And that's what we want to do. So what Kripke argued is that circularity is present in everyday life. Most natural phenomena are cyclical movement of the earth, right? I mean, the solar system goes in cycles forever. Our digestive system works in cycles. I mean, eventually a person dies and it ends, but for all practical purposes, we can assume that it will keep going on forever. Social interactions, so we cannot model all these things using standard logic because standard logic is all essentially supposed to be well-founded or inductive. So if you look at a conversation, really a conversation is a circular phenomena. The first speaker speaks, and then the second speaker speaks, and then the conversation recursively continues. Shared conventions are cyclical concepts. So for example, we all drive on the right-hand side of the road, but we are implicitly assuming that everybody is following the same convention and they will also drive on the right-hand side of the road. If everybody did not sort of implicitly agree to this convention, then we'll have chaos. Then another interesting thing, for example, if I make this statement, so Jack and Jill are very much in love and they go to a party and, well, they state that. So Jack says, I will eat only if, Jill, you eat. And Jill says, well, I will eat only if Jack, you eat. So the question is, will they eat or not eat, right? So again, this is a circular thing. And it arises all over the place. And you can find numerous other examples. So circularity in computer science, of course, arises in many, many places. We have circular linked lists that we talked about, graphs that have cycles. We have controllers that run forever, like that automata, omega automata. Bisimilarity, right, is a circular concept. Interactive systems where the system really runs forever, right, where you're just interacting with the system and keep clicking on it and doing things. Automata over infinite strings, script case structures, perpetual processes, and logic programming is really not equipped to model these circular concepts directly. So we need what's called co-induction essentially co-induction is a proof method for sort of circular infinite things. So circular structures really are infinite structures. So if I write x equals 1, 2 vertical bar x, which essentially means that x, here it means that x is rest of the list. So think of it again as a circular list. Logically speaking, this is an infinite list, 1, 2, 1, 2, 1, 2, that goes on forever. Right? So really when you have a circular linked list, it's an infinite list, repeating. And so proofs about their properties are going to be of infinite size as well. And co-induction is really the technique for proving these properties. So the first person who actually looked at it was Peter Axel, and you can actually find his monograph from the 70s or 80s. And it really relates to co-algebras and category theory, where mathematicians who study category theory study algebras and induction, also study co-algebras and co-induction. And so another thing I wanted to mention is that if you look at infinite behavior, then there are two types of infinite behaviors, what you could call rational versus irrational. So it's like rational numbers, right? If you have a rational number, say 1/3, then you have 0.333. So that 3 is repeating. Yes?
Sorry to pick up on you. Circular structures are patently finite. So there's a difference between not having end and being finite.
Absolutely, yes. So true. But they really are infinite with a repeating pattern, the pattern that is repeating. So now so that's how in standard logic you deal with it is by, right, for example, when we write programs with circular linked lists, we try to find the end of the list by checking that we are back to the same spot.
What bothers me is that periodicity is much simpler phenomenon than infinity. So if you go to combinatorics, they deal with periodicity all the time, and they don't deal with infinity. It's much harder.
I see.
So mixing the two may not.
Sure, absolutely. And I mean, we certainly should discuss that. Yes, absolutely. So our interest here, as I will show you, is that we want to obtain an operational semantics for co-induction. Just as recursion gives you an operational semantics for induction, in inductively defined programs, I want to get an operational semantics for co-inductively defined programs. So if you look at infinite structures, then they're either rational or irrational. Rational basically means that they're infinite, but there is a repeating pattern. So there are a finite number of repeating patterns that appear infinite number of times, like in an omega automata or a Kripke structure. Whereas irrational infinity is really like, really the behavior does not repeat at all, just as in rational numbers and irrational numbers. So again, if this book, which is Circles by Moss and Barwise, really is a very comprehensive description of co-induction. And what we are interested in is how co-induction can be realized in logic programming and theorem proving, but mostly focused on logic programming. So let's look at co-induction, what co-induction is. We all know induction. So induction is a mathematical technique for finitely reasoning about an infinite countable number of things. Example of inductive structures, again, you already know this. Natural numbers, 0, 1, 2, etc. All finite natural numbers, all finite lists. And how do you define an inductive structure? It has 3 components. You have the initial condition. You essentially also talk about iteration. You talk about how you build the next bigger structure. And you're interested in the minimal set that satisfies, that you can build under these 2 operations. So for example, if you want to build lists, initiality and the condition for list, empty list is a list. And then if I have a list T, then H const T will get me a bigger list. That's iteration, right? How do you build the next element? And then I want the set of all finite lists as, the part of the inductive set, that can be built using these two operations. So that's our standard inductively defined set of lists. Co-induction is a mathematical technique for finitely reasoning about infinite things. It's really a dual of induction, and it has two components. So you drop the initiality condition, no base case. Okay, so you have iteration and maximality instead of minimality. Now you have maximality. So for example, if you want to define the set of lists, then all you say is that if T is a list, then H const T is a list as well. So now this operation really describes all infinite sized lists, right? So I have an infinite list. I add one more element to it. I have another list, right? That is also infinite. And I'm looking for the maximal set. So this co-inductive, if you take the co-inductive interpretation of this operation, then it really specifies all infinite sized lists. So natural numbers, if I define natural numbers in this manner, that 0 is a natural number, and I want to build the set S, if X is in set S, then X plus 1 is also a natural number. Then I can have a least fixed point interpretation and a greatest fixed point interpretation. The least fixed point interpretation will give you all the finite, right, elements of all finite natural numbers. The greatest fixed point will also include omega, the infinite element. And you can think of omega being defined as omega equals a solution of the equation omega equals omega plus 1. So now when we give least fixed point semantics, we use induction as the proof technique, and we basically use recursion as the operational semantics. So least fixed point semantics, induction, recursion essentially are all equivalent sort of. The dual is you have greatest fixed point, co-induction, and co-recursion. So what is co-recursion? You can think of it as recursive definition without a base case. So there are no base cases because you're only talking about infinite structures. And then there are many applications I think I already mentioned. So if you could look at standard logic programming, it's actually inductive logic programming in the sense that it uses, it essentially computes inductive sets. It defines inductive sets. Now, inductive logic programming has another meaning if you're familiar with it, which relates to machine learning logic programs from examples, but I don't mean that inductive logic programming. Essentially, given a logic program, taking an inductive interpretation for finding the meaning of this program. So it's useful for writing programs for reasoning about finite things. You can have finite data structures, and you can essentially compute finite properties, verify finite properties. So clearly then traditional logic programming will be unable to reason about infinite objects and or properties. So let's say the glass is only half full. We're missing the part where we can actually deal with infinite objects. So here's an example. So suppose I have a program that defines a bit stream. So this is a recursive program. So you have 0 and 1 are bits, right? Those are facts. Then I have a co-recursive program, no base case, as you can see, which says H const T is a bit stream if H is a bit and recursively or co-recursively T is a bit stream. And then I want to, given X equals, so given a circular list, which is X equals 0, 1, 1, 0, cons X, or vertical bar X, comma bit stream X. So I want to check if X is a bit stream. I would like to have success because this is really an infinite stream, a bit stream. But Prolog will go into an infinite loop because the structure is infinite. So what we'd like to do is to add co-induction to logic programming. And you can actually give semantics. Once you add co-induction to logic programming, then the semantics is actually the dual of the inductive semantics. Instead of looking at Herbrand model, you have the co-Herbrand model. So how does Herbrand, again, this, it doesn't matter if you don't understand this, but if you know logic programming semantics, then this will make sense. So in the Herbrand universe, you add all the infinite terms as well, because the Herbrand universe has only finite terms. You add infinite terms, you get the co-Herbrand model. And then the meaning is given in terms of greatest fixed points, and you're computing the maximal model of the co-Herbrand universe. So again, if you're not into logic programming semantics, it doesn't matter if you. So what I'm really, okay, let's skip this. So what I'm really interested in is giving an operational semantics to co-induction. Just as you have a logic program and you pose a goal, and SLD resolution gives you the operational semantics for Prolog or logic programming, where you have a goal, right? You find the matching rule, and then you replace you perform unification, and you import the bindings, and you replace the goal by the body of the matching clause, right? That's operational semantics. Then you go left to right, and then backtrack if something fails. What I want to do is to give an operational semantics to co-induction, which we call co-SLD resolution. It's actually very simple. All we have to do is recognize cycles and succeed. So how do we describe the operational semantics of a logic programming system? It's basically a non-deterministic state transition system, right? Where state is a pair of, you have a finite list of goals, right? You have a set of goals, your current resolvent at any given moment, the list of goals you have to solve. And you have a set of bindings, right? Bindings are of the form either x equals f of x, or a circular, right, structure here, or simply x is a term that does not contain x. So it's very simple, right? We have a set of goals and a bunch of bindings. And I'm going to simplify, pick up a goal from this list, expand it, and keep moving. And you have transition rules, which are the definite clause rules under standard logic programming, which essentially find a matching rule, perform head unification, and then the unification succeeds, and you replace that goal with the body of the clause, right? And then apply the bindings to the rest of to the continuation of that goal that was replaced. So to that so if we want to get operational semantics for co-induction, so not only we have the definite clause rule, but we also add what we call the co-inductive hypothesis rule. So the co-inductive hypothesis rule goes like this. If a co-inductive goal G is called, so we declare certain goals or certain predicates to be co-inductive, which means we'll take the greatest fixed point interpretation of them. If such a goal is encountered, then we'll go up the search tree that is built, the SLD resolution tree that is built. And if I find an ancestor call that unifies with the current call, then I succeed, because I'm basically recognizing that I have a cycle. And if I see a cycle, I succeed.
So what if the sub-goal is more general?
So here comes an example. So that's the main thing. Okay, so it's a simple example. I have goal G, and I execute, and I see G again. So G matches with G, I succeed. Okay, so now...
But do you mean matching or unification?
Actually unification. So suppose I have this very simple program, P if P. So as you can see, the least fixed point is actually empty. This program cannot compute anything because there's no base case under inductive semantics. But under co-inductive semantics, if I call P, right, it's basically an infinite chain. It's a cycle, so it should succeed under the greatest fixed point semantics. So with this operational semantics of recognizing a cycle and stopping, so if I call the query P will call P in turn, and then it matches with the ancestor call, succeeds, recognizes a... Okay, more interesting case. If I have P of 1 const T if P of T. So this program really defines an infinite list of ones. No base case. Now suppose my query is P of X. Then X will succeed. So I can draw this. So I have P of X. I match X becomes 1 const T. Right? And my next call is P of T. P of T and P of X will unify. We get T equals X, and I terminate. What is my answer? The binding of X. And what is X? X equals T, which equals 1 cons T, which equals 1 cons X. So what is my answer? My answer is X equal 1 cons X, an infinite list of ones. Right? So not only it recognizes cycles, but it'll also produce circular structures as answers. Okay. So it doesn't matter whether it's less general, more general. If it unifies, you terminate. Unifies, you import the bindings, you terminate. And if there were other goals after, P of X comma something which refer to X, then at this point X has a binding which is infinite list of ones.
There's a difference between inductive and the co-inductive case. In the inductive case, the answers are recursively linear.
Inductive case, the answers are...
So the set of facts you can learn are innumerable. But for the co-inductive, you're giving a procedure that will give some set of answers that are solutions, but it's going to be complete with respect to its definition. What definition is it? Does it match?
Good point. But see, again, because we are restricting ourselves to, rational infinite cases, to cycles.
That's what it finds.
Yes,
but it's not finding the irrational.
No, it won't find the irrational. We need some other termination. As you can see, it all depends on the termination criteria, right? My termination criteria is very simple. If I see a cycle, I stop.
Yes.
So I can only find. So if you have a different termination criteria for characterizing other types of infinite behaviors, for example, numbers 1, 2, 3, 4. Then I could terminate on that as well.
So what did Prolog 3 do in this case? Didn't it have rational
So
trees?
Prolog 3, yes, it did have rational trees. Honestly, I don't know what but it may be that as long as you only explore the finite part of the tree, you're okay, just like in lazy evaluation in functional languages, right? As long as you only explore finite part of the infinite structure, there's no problem. That's what Prolog 3 probably had. Again, I've not looked into that. But here we're trying to actually be able to, and again, you'll see more examples. Sure, go ahead, sorry.
Sorry, because I don't understand the Prolog, but I've been used co-induction in Cox. In Cox, there's usually a Gardner's condition for the co-induction. So I wonder what's that in your case here? You don't need to worry about the Gardner's condition. Can you define omega in terms of omega itself?
I don't know. I'm really not familiar too much with Coq beyond superficial. I think the guardedness condition, I suspect, is that we're limiting it to, for example, just lists or. So, for example, if I wanted to program something like this in Coq, I don't know how you would do that. What would be the guardedness condition?
It would be that you can define a list to be something, for example, h const x to be h const x, but you cannot define x to be x.
Because you need productivity, right?
Yeah.
So
you just don't need productivity.
Yeah. And there are other people who have extended it to productivity and all those things. So here, if you say P of x if P of x, I'm perfectly happy to terminate. Okay.
So I think you build productivity into the rules themselves.
That's right.
So if you fire a rule, you're productive.
But people have actually extended this idea. So Ekterina Komanskaya at Dundee has extended it with productivity, and she's done all kinds of work extending this. So this is 10-year-old work. A lot of people have extended and worked on it.
Are you guaranteed to find circularity if there is one? No.
Sorry?
If the situation is circular, are you guaranteed to find it?
Yes, so let's come to the under the appropriate. So remember that you are searching in Prolog under the appropriate the search regime that you're using. So as long as you guarantee, say, breadth for search, then eventually yes, you will find it as long as it is rational infinite. So here is the. So I'm not going to. So co-inductive logic programming is really the dual of table logic programming. Again, if you know what table logic programming is, so as you know, Prolog has difficulty in terminating when you have left recursive rules, and table logic programming helps you in finding terminating even when you have left recursive rules. So if you have purely inductive semantics, then co-inductive interpretation will fail. And if you have purely co-inductive semantics, then wherever table semantics fails, co-inductive will succeed and vice versa. So really they're dual. So again, this is something very technical. So you can actually prove soundness and completeness theorems that if there is a goal the element of the greatest fixed point, then co-SLD resolution will find it. and completeness as well that, sorry, the other way around. If we find something as a result of co-SLD resolution, prove something, then it will be in the greatest fixed point, and the other way around, that if it's in the greatest fixed point, as long as, rational proof is very important, that we're only looking at rational proofs, that the cycle is important. I mean, we can't find anything for irrational stuff unless you, change things.
But in the soundness, do you guarantee that the result is rational?
Basically, whatever it computes is going to be in the greatest fixed point.
But,
right.
But is it also, but for soundness, don't you get rationality as well?
I mean, rationality is sort of built into the co-SLD resolution algorithm, right? Because you only terminate if you see a cycle.
Right, but isn't it, I was expecting that you had a condition that you capture rational solutions.
So essentially you
can it ever produce a non-rational solution?
No, it cannot, because then you will never terminate, right? Because the termination is based on unifying with an ancestor. So the solutions will only be rational terms because of the way the algorithm is designed, indeed. Yes. And then you can write a very simple 7-line meta-interpreter for realizing. And so the joke in my lab was that actually Luke Simon's PhD thesis was just 1 page, because that's the meta-interpreter that describes. So actually there's a more sophisticated meta-interpreter available from my homepage, and co-induction is actually now available, has been available for many years in SWI Prolog, and YAP is another Prolog, and there's another logic language called LockTalk, which comes with a whole bunch of library of examples. So many more people have worked on this. After we published the first paper back in 2006, and all that work is available. Okay, so let's quickly look at. I want to get to the application of AI as well, of co-induction. So here is simple illustration. So we have this program which basically describes a stream, very similar to bit stream. H const t is a stream if H is a number and T is a stream, and number is inductively defined. 0 is a number, n plus 1 is a number if n is a number, and then if I say I want to basically check if 0, 1, 2 const t is a stream, and I want to get bindings for t. So the way the execution algorithm works is that you start expanding using this clause, right? The first one, no base case, as you can see. And then at every step, you have to remember the call. You have to memo the call. And then at every step, you have to unify with all the ancestors. So you can see it can be expensive. So here, since I have 3 values, I'll have to recursively go down until I reach the tail, the rest of the list, reach T. So when I reach stream tree, then you will see that it unifies with this ancestor call, and this ancestor call. And you'll basically get solutions, with the first one, you will get this solution. Second one, you will get this solution. Third one, you will get this solution, right? I mean, unifying T with this, and that. And then the fourth one is I can expand T again. So I can get more solutions. So you can get infinite number of solutions. So now what about, applying things like append and member and all those things to infinite lists? So here's a simple program for appending 2 lists, which is really simple. Okay, so base case is kind of in gray. Appending list X to an empty list results in X. Appending a list Y to a list whose head is H and tail is T is the list H const Z, where Z is recursively obtained by appending Y to T, right? Very standard recursive definition. So now if I say Y is a circular list and append this circular list to the finite list 1, 2, 3 and get the answer in Z, this is what I'll get. I'll get Z is got a finite handle 1, 2, 3 const Y, where Y is a circular list. So it's really 1, 2, 3, 4, 5, 6, 4, 5, 6, 4, 5, 6 forever. And it actually works, no problem. Okay, what about more interesting cases? When the first argument is a circular list, I'm trying to append a circular list to another circular list. Right, so X equals 1, 2, 3 cons X, Y equals 3, 4. Right, really, this is not a cons, vertical bar Y. And then append Y to X to get Z. So X and Y are both circular lists. The answer using the algorithm or the co-SLD resolution will actually be Z equals 1, 2, 3 cons Z. Okay, which is surprising. But if you think about it, this list really represents the infinite list, and you are really appending to infinite lists. So you will never really be able to get to Y.
It's not transfinite.
Yes, and then if you say, well, I should be able to say member 3 comma z and get a success, but that would be an irrational proof. So, okay, so basically I can justify it away. But the more interesting thing, yes?
You mentioned that you get omega, but here it seems like you get omega plus omega.
No, you're not kidding. He's staying inside.
Yeah, I mean, the answer is still omega.
Because you push for the unreachable part.
Right, so, I mean, so basically, if when I append x to and y will become unreachable, and it is unreachable. Okay, that's all I can say.
Is it obvious that this was the intent?
No, it was not. So
sort of backward. That's our solution. Therefore, that's what we wanted.
I mean, again, you see surprising behavior. I mean, there are lots of. The moment you start dealing with infinite things, you're operating in a crazy world, and you try to make sense out of it. Honestly, yes, it is exactly like that.
So another point.
Sure.
You consider just co-induction or both induction and co-induction?
In this one, I think it's just co-induction, I believe.
And in general, you put both?
But you would do both, yes, yeah.
So
you will expand as well, and you will succeed.
Greatest fixed point of minimum, of smallest fixed point?
Yeah, so you could argue that the greatest fixed point contains both the least fixed point and the infinite terms. So I want to find both.
No, I think, what if you have annotate predicates by, I want this.
Yes, that's what we're going to do exactly, inductive and co-inductive. Yeah, you guessed it right, yes. So now what about, Prolog can reverse, right? So if I give the value of z, it will give me all x and y such that when I append x and y, I get z back, as you know, right? Prolog programs are reversible. So if I say z is 1, 2 const z, and I call append x, y, z, then actually it does give you answers like x is empty and y is a circular list. Then it will start giving you x equals, basically start giving you all finite prefixes, and that's a problem that, it will basically there are infinite number of solutions. X equals the finite list 1, y is 2 const z, where z is the circular list or the infinite list. And then it will keep producing this x. It will also produce x equals 1, 2, y equals z, and it will produce 1, 2, 1. You see the problem, right? And that actually is a big challenge. But it does produce this answer as well. X is infinite and y is some whatever. Okay, so now the interesting one is member. So this is where you're talking about you do something and you figure out, oh, this looks strange. So if I define member in this way, I say member H is present in a list if it's present at the head, right? So that's the base case. Again, it's in gray because we're not going to use it. And then H is present in the list x const t. Right, x is not the same as h, then it should be recursively present in T. Now suppose I ask this query, L is the circular list 1, 2 const L, vertical bar L, is 3 present in L? It should fail, right? It actually succeeds. Why? Because, if you use this recursive unfolding, then it will skip over 1 and 2, and eventually you'll get to the call member 3, L, and now it will co-inductively succeed. Yes?
I have a question I wanted to ask earlier. Didn't want to drag it into foundations. So when you say co, it has a precise meaning in category theory.
True.
Now,
and
if you
I'm
don't
not a category theorist, I'll tell you that, yes, yeah.
Yes, so if you don't have category theory background, all this co becomes a little vague.
It's quite possible. I'll tell you this, that the category theory people are so excited to see some practical use of their work that they invite me to their talks all the time. And I go to their talks and I cannot understand a single, honestly, I cannot understand a single talk that they give, but they're really excited that there is something practical.
This is a different story. You may be very successful, wonderful, congratulations. But to understand,
sure.
When if I'm not a category theorist, but I know I use some. So if you tell me some notion and then you say co, I know exactly what you say. I just reverse the arrows.
Absolutely.
Right. Now here you say co-induction. I have no idea what it means. It's kind of vague idea.
So the category theory people have actually tried to put what I have presented to you here in their own language. I can send you that stuff. You can, if you just Google, you'll even find it. So, and again, I'm not a category. My interest is very practical, to be able to reason with infinite terms. And so I can send you that pointer where category theorists have tried to explain this in terms of category theory.
And did they succeed?
I really am not equipped to answer that question. You decide. I'll send it to you. Okay, so now it succeeds, so that is counterintuitive. And anyone see the problem? This membership question is wrong, because membership in an infinite list really should be, is 3 present infinite number of times? We're asking, this is basically asking, is 3 present once, so to speak? So what we really need to do is to define it in a different way, and to define co-member. Co-member will be X is present in L. If I delete X from L to obtain R, then recursively or co-recursively, X is again present in R. So is X present infinite number of times in L is what should be the real membership question in an infinite list. And then it works nicely. So if you define it in the drop is going to be inductive, so you need tabling for that. Now if you say X equals 1, 2, 3 cons X, is 2 a co-member of X? It will say yes. If you give a finite list and say, is 2 a co-member of X? It will say no, because 2 is not present infinite number of times. And if you say X equals 1, 2, 3 cons X, is Y a co-member of X? It will actually give you the values, just as Prolog would for the finite case. And if you say X equals 1, 2 cons vertical bar X, is 3 a co-member of X? And now the answer is correct. It says no. Right? So this is really, kind of, so we struggled with this, and it's sort of cool that, it actually works nicely. Yes, yeah.
So what about the situation where you have an infinite list which has a finite prefix, which is different from the periodic part, and you want to express
that's not a problem. Yeah,
Okay.
it'll work with that.
Okay.
So your co-inductive, I mean, we actually had that in the append, where it produced, when we take a finite, no, where was that?
I think it's z equals 1, 2, 3, y, and then y is 4, 5, 6, right?
Y, so that is, y is the circular list, z is the finite list 1, 2, 3, and you will get the answer z has a finite handle 1, 2, 3, vertical bar y, where y is a cyclical.
Yeah, exactly. So then if I ask, is 2 a co-member of z, the answer is no.
Answer is no, yes.
But anything is a inductive member of z. So how can I express the predicate, is a member of z precisely once in a co-inductive fashion?
Or at least finitely many times.
Finitely many times.
I think possibly then you will need the base case, because you're looking for something inductive. Moment you add the base case, yes, of course, once you reach the head, I mean, that element will be head of the list, and the base case will succeed and give you the answer.
Right.
So you're asking an inductive question, then you need to add the base case then. Okay, so as you can see, it really is very elegant. I mean, you might still have objections, but it really is, at least from logic programming perspective, all these algebraic properties, quote unquote, are preserved. So of course, now you can have co-logic programming, which combines traditional logic programming with co-inductive logic programming, essentially syntactically identical to traditional logic programming, except that now predicates have to be either declared inductive or co-inductive. And then they have their own semantics. And then, of course, the trouble is that if you have induction and co-induction mutually recursive, you are in trouble. Exactly why I think, right, you can't have least and greatest fixed point, sort of cyclically present in mu calculus expressions or something. So anyway, we don't have to go. So now if we look at the nature of computation, so then there are 2 types of computations you could argue. Those that are well-founded, and these are really inductive computation. You start from a call based on computing the elements of the least fixed point, implement them with recursion. You start from a call and you terminate when you reach the base case, right? So that's well-founded computation. And then you have co-inductive computations, which are really consistency-based. All you're trying to do is to determine that your logic or your elements are mutually consistent. So if we combine these 2 things, then any computable function can actually be, so this statement is without proof, I claim, or hypothesize, can be programmed very elegantly. So you can implement modal logics like LTL very elegantly, I claim. And then, so I will show you a one-slide implementation of LTL in a few minutes. And then complex reasoning systems can be built like non-monotonic logics, which has applications in AI. So here's my pictures that, you have the edifice of computation that only rests on the pillar of LFP or induction. And GFP is simulated by using negation over LFP. But if we use co-induction, we can really make it stand nicely. Okay, so very quickly, one example, then I think I'll jump to the application of co-induction to AI, why it's important for AI. Okay, so here's a description of an automata, where we say we want to program this automata essentially, find out if this automata accepts some string or not. So this says x const t in state st will be accepted. So this is the list of symbols. If there is a transition from state st on symbol x to a new state, and recursively t will be accepted in the new state. And then you say, if I reach the empty list, the end of the string, and I'm in state st, then st is the final state, right? So very elegantly. So logic programming is very good for describing language processors. And you can see that power in 2 lines. You describe if the essentially model of an automata. And then I have this automata modeled here as transition relations, and S2 is the final state. And if I ask, give me all the strings x such that x is accepted from state S0, logic programming will actually give you all finite lists, start. Now let's make this co-inductive. Drop the base case. Now what will happen? It'll actually tell you all the cycles. So it will start giving you cycles as answers. Now the problem is that it will give you also the answer x equals ABE, comma ABE vertical bar x, and ABE, ABE, ABE vertical bar x. So it starts giving you, and that actually is a challenge. Here's an interpreter for LTL written in, as it's promised, 1 slide, where essentially it's a verifier. You're checking if a LTL formula holds or not. And it's actually very easy to extend it to, there's real-time LTL as well, because you can model time using constraints. We actually have a paper that extends this description of LTL verification, formula verification, to real time, where you say that if I see A, then B must appear within 5 units of time or something like that. So you can see that the greatest fixed point operators, based operators like global, release, are co-inductive, and the least fixed point based operators, future and until, are inductive. And you've got or, and all those things. And you can see this on the side. So in one page you can write, and now we can solve the problem that got us motivated here. We have timed automata, and I can actually model the automata as a logic program, and so basically this automata says that reset the stopwatch C when the approach signal comes, and then in can only be seen when at least 2 units of time have elapsed, and basically have to show that your design is safe, that the train in the gate area, gate will always be down. So you can model the constraints, the time, the timing constraints using constraint logic programming, and you're actually not approximating them with something finite. You're truly modeling continuous time. So that's a great property of CLP, of this way of modeling timed automata. And likewise for the controller and the gate. And now I can build a driver sort of combines all these systems. So it calls a train automata, gate automata, and then it calls recursively the driver. So basically simulating the automata, just like I showed you that. And now, but there is no base case. And now I can co-inductively check for properties. And basically you can do all the safety, and you can use it for verifying the deadlock freedom of the dining philosopher's problem. But here you use basically tabling and induction. But I can prove liveness properties as well. If you have this model of each philosopher has a stopwatch, and the philosopher who waits the longest gets to eat, when there's a conflict. And you can, using co-induction, you can verify there are many other applications as well. You can model, you can develop omega push-down automata, omega grammars, cyber physical systems, and you can also use co-induction to build predicate answer set programming systems that are very useful in AI. So I'll take 5 more minutes and I'll stop. And so my claim is that co-induction is really crucial to AI success. So we have all this buzz about machine learning and AI, But it all depends on training data, how good your training data is, huge amount of work. Eventually, you need common sense reasoning in a real AI system. You need to be able to handle common sense reasoning, and that only works with co-induction. And I'll show you why in a second. You can model cyber physical systems as well. Logic programming is a very good way of modeling cyber physical systems. You can model discrete computation with standard logic programming. Continuous physical quantities model via constraints. Concurrency model via co-routing in logic programming, and something running forever model via co-induction. So we actually, again, tried this and basically showed, this is from Hensinger's paper, where they were trying to establish some parameter to establish the safety of a nuclear reactor system or something. And we basically showed that using our method, you can actually essentially get a better value of the parameter that they were trying for. So again, all these are in papers, a whole bunch of papers. And many other people have done work as well using co-inductive logic programming, co-inductive type inference in object-oriented languages. These guys won the best paper award at eCoop that used co-inductive logic programming. And then I was talking about productivity. That's Ekaterina Komendantskaya at Dundee. She's used it. And Dexter Kozen actually has imported these ideas to obtain what's called co-camel. Essentially, it's Haskell or ML with co-induction, really. Very similar ideas. And other people have worked as well on various things. So co-induction. So 3 more minutes and I will stop. So I want to put forward my spiel about why co-induction is important for AI. So co-induction is crucial to automating common sense reasoning. Why? Because given a situation, we modeled using statements in logic. So these statements may have multiple models, each representing a possible world. So if you consider, you've seen this example. So it's a Jack eats if Jill eats, and Jill eats if Jack eats. Really what we had with this if and only if statement says Jack eats if and only if Jill eats. So that's a formula. You treat it as a propositional formula. You can find the models. There are 2 models, right? Either both eat or none eat. Straightforward, right? So as long as we're in the propositional world, there is no problem. So if you set solvers for each model is a possible world, and you can work with it. Suppose we want to generalize it. We say X eats if Y eats, and Y eats if X eats. And generally, so when we go to, the reason we want to go to predicate logic is we really want operational semantics. We want to be able to write rules that say Y will eat if X will eat, or rather X will eat if Y eats and some other condition, and Y eats if X eats. So we really want to be able to write them as programs. But the moment we do that, we get into trouble because we have cycles. And if we use inductive semantics, basically we're at a loss. But co-induction can help. And if we introduce negation, which negation is failure, then life becomes even more complicated, and you need negation as failure. So consider this jury decision task in a murder trial, where individual A has stabbed individual B. So it's actually from a real case, real paper that psychologists were examining. Suppose we want to automatically arrive at the decision. We want to model the jury decision process. So there are all kinds of things you have to consider, right? You state the situation, using formulas. And then you want to conclude whether A should be found guilty or not guilty. And there are things to consider, such as A was afraid of B because, he had a prior fight, and they were going to be at the bar at the same time or something, and he took a knife to the bar in self-defense. Or it could be that A is a revengeful person who took a knife to the bar because, this guy's a tough guy, and they had a fight before or some altercation before. So there are many competing hypotheses. And what we want are formulas that we express, this knowledge to be able to give us these multiple hypotheses. Each hypothesis is a possible world, right? And these hypotheses can only be produced if you have co-induction, because if you have inductive semantics, there'll be only one answer, only one fixed point, the least fixed point, right? Only one model. So really what you have is that each scenario has information which is mutually consistent and will produce a guilty or not guilty. And each scenario is a solution to a set of co-recursive equations. The moment you establish a fact, you know that, basically well, this guy is revengeful. You can immediately conclude that, he should be punished. But you conclude that if he was, he did it in self-defense, then he should not be punished, etc., etc. So much of common sense reasoning is very similar to above. And you really, as I said, you need co-induction. So co-inductive logic programming has been used to give operational semantics to predicate answer set programming as well. Answer set programming is really an extension of logic programming that allows negation as failure. It allows you to simulate various mechanisms used in common sense reasoning. I don't know if you're familiar with default reasoning, non-monotonic reasoning, abductive reasoning, counterfactual reasoning, preferences over defaults, and all sorts of complicated things. And actually, a query-driven predicate answer programming system was thought to be impossible to build, but co-inductive logic programming made it possible. So you can actually download this system called SASP. It's an implementation of answer set programming. Answer set programming is really a very sophisticated paradigm for reasoning, symbolic reasoning. And it actually is query-driven, and it has been used to simulate expert knowledge for many applications. It's actually been used to develop a system for treating congestive heart failure, and it actually shown to be outperformed the doctors because it models human reasoning very closely. And also, we're working on developing a natural language question answering system because you can represent common sense reasoning. It actually takes a passage, translates the knowledge into an answer set program, takes the words in the passage, goes to WordNet, obtains all the common sense knowledge about those words, converts it into an answer set program, takes the question, converts it into an answer set program, and then you can answer the question. It actually compares very well with learning-based approaches. And of course, since it's based on actually understanding the text, with a little bit more work and a little bit more knowledge, it can easily outperform any machine learning-based system. Because machine learning-based system is like, you go to an exam and you really never studied for the exam. And so you're basically doing guessing, right, based on pattern matching or whatever, right? That's what machine learning really is when it comes to answering natural language questions. But if you understand, you can really answer. Okay, so to conclude, we talked about circularity, how circularity is a concept that occurs in everyday life and computer science. Logic programming is unable to cope with circularity. And the solution is to introduce co-induction in logic programming. As you can see, co-inductive logic programming, co-induction is a powerful concept. Applications to verification, non-monotonic reasoning, negation in logic programming, type inference. So if you want to build co-inductive type inference engines, you can use co-inductive logic programming. Really, the type inference engine of most functional languages really is a logic programming engine. Hybrid systems, cyber-physical systems, common sense reasoning. You can actually obtain the very sophisticated meta-interpreter for co-inductive logic programming from my homepage, as well as the distribution of the SASP system. There's actually another extension of SASP with constraints called S of CASP. So the S is tongue-in-cheek, successor of ASP. So successor of CASP. A lot of information on my homepage. So thank you very much for your time, and a lot more information on my homepage. And I'm happy to take any questions.
Thank you.
Yes.
Not to diminish from your practical work, but the propaganda sounds to me so 1980s. Logic programming, I thought it was long dead. Logic used as a basis for AI.
Yes.
So many dissertations were written.
Absolutely.
Today, I think there's not a single qualified AI guy who buys that. Maybe in 50 years.
No. I mean, so you're right. I mean, again, so that's basically been that there's a lot of focus on, what is called good old-fashioned AI, right? Rule-based reasoning, knowledge representation. I mean, so the work has kind of gone on, and no matter what you do, I mean, you cannot banish logic, really. So what is really succeeding now, so and of course now the world has moved to machine learning, everybody's enthralled with machine learning, deep learning, and deep learning is going to solve, practically every problem, and every day somebody will contact, even if they want to add 2 numbers, they want to use machine learning for it, or deep learning for it. So but the work has kind of gone on, and you could say, so answer set programming really is you could say the state of the art when it comes to knowledge representation, as I said. So I'm really hopeful, with this work that I talked about. So it's a whole other talk, unfortunately, no time, where I am, let's say, 99% confident that we can produce a common sense reasoning system that can actually answer. So there is the Alexa challenge, right? I don't know if you know about it, where it's essentially anyone who can. So Amazon is organizing this competition where you basically build a system that can hold a conversation, run it on Alexa, holds a conversation with a person for 20 minutes, like a human. And so we're basically working towards that. I'm extremely confident that answer set programming and this goal-directed implementation of answer set programming will take us to the promised land of common sense reasoning.
IBM did exactly that.
No, IBM says the same old application of Watson. Same old application of Watson. Now it's for debate or something. I was listening to the news yesterday. Is marketing. Watson actually. I'm sure you all are Microsoft guys. I'm happy to hear that. So I can say I can criticize Watson. Okay, very good. So Watson. So what really Watson tries to do is, right, as you know, the idea is that I can feed it millions and millions of pages of text. So this is a superhuman who digests everything and can answer questions. But there's tremendous amount of training involved. So Jeopardy, it worked out well because you had 30 years or 40 years of all those questions. So they actually applied this to cancer research in, as you probably know about it, MD Anderson Cancer Center, sunk in $60 million. The result was, and there is paper that documents that, the result was, I think that for simple cases, it's 70% success, and for complicated cases, only 30%.
Unfair in this case. So this Israeli group in Haifa, IBM, and they, I read a little paper of theirs, they are not Watson. They have various ideas in recent AI learning, which is much beyond Watson.
Sure, but we're talking about Watson here, right? So
you're talking about Watson.
Yes. No, you said you heard it on the news, right? You heard it on the news. So Watson is limited. I think so. I would argue that any machine learning based approach is going to be limited per se, because it's only based on training data. You need common sense reasoning. How are humans able to perform, much better than any AI system? Because we got all this knowledge that we have, acquired over the years. Things like, if I see this bag and it's lying on the table, then I know it's not going to fall through, or what kind of things it might have inside, right? We know all this, so you have to model all that, bring in all that. And once we do that, now you'll say, well, there was a Psych project, right? All of you probably know about the Psych project, CYC, Psych project, and in Texas, yes, actually in Austin. And the reason actually Psych project failed was that is again so the problem is that if you look at, people have been resorting to classical logic. Classical logic has many problems when it comes to simulating common sense reasoning, because we humans make inference, as I was telling Nikolai, not only based on, say something like modus ponens, but also on when there is information absent, then we still make a decision. So I call my friend text my friend, he does not even immediately respond. Normally he responds very quickly. I know that, he might be in the shower.
You attack the point nobody defends.
Sorry?
You attack a point that nobody defends.
So, what I'm saying is that you need common sense reasoning. And common sense reasoning can only come through logic. So we're looking at classical logic, and now we have to look at other kinds of logic, which is what answer set programming provides, non-monotonic logics.
Let's say, with a danger to bore people, publish a reasoning, 4-stage reasoning in a newspaper. Most of people will not buy it. Even it will be very clean reasoning.
Sure, absolutely.
And not because they're stupid.
Yes, yeah.
Because a clean, logical reasoning has tiny domain, pure math. Okay? So in the real world, we're so much aware of things that all rules are breakable and so on.
Sure.
So I'm a logician, but promoting logic as a foundation of AI.
No, I am not promoting classical logic as a foundation of AI.
Right.
Because answer set programming will let you model non-monotonic logics. You need non-monotonic logics because what happens, exactly as you said.
I don't, because it's completely impossible logic. It's complexity beyond any reason. The people who work in non-monotonic reasoning never...
I mean, we can argue, but I mean, we're not looking for perfection. If I can perform 80% as good as a human, I've achieved quite a bit.
Okay, now you're talking.
Right.
And that's what AI does.
No, I would say it does much less, because anytime something has an intelligent feature, first thing I want to do is to shut that off because it's not conforming to my intuition. So most of the time. So it needs to be better. And again, I think the salvation is in common sense reasoning, non-monotonic logic, answer set programming. And I'm working towards that. So other questions, sorry.
Good luck.
Well,
Okay,
thank you.
Thank you.